this computer. Okay. Then let me share these. Okay. So thanks again, everyone, for joining us on this series of tutorials. Today is day 5 of the RH course. And today, let me see if this moves. Yeah. And today we are going to learn how to compute spectral lines in LTE with RH. We focused the first tutorials on the non-LTE part. That was the novel part of the code, but it's also necessary to do the computation in LTE for some lines. And the idea is that when you have a non-LTE transition, in general, they are very broad. So you can expect at least some photospheric lines to fall on the wings of the non-LTE transition. Or you can also have multi-wavelength observations where you have some photospheric lines that are sensitive to the magnetic field, for example, and you want to combine the inversion of the synthesis with the non-LTE lines. So then you don't need to solve the non-LTE problem for those lines. So what we are going to do is for those that are well treated in LTE, we solve the problem in LTE, and then we solve the problem in LTE for the rest of the lines. The basics are very similar to SER and also design. We will provide a file that contains the atomic information of the transition and a wavelength vector for seeing. For letting RH to compute the atomic populations of those transitions in LTE, and then RH will combine the results from the non-LTE solution for the given atom with those from the LTE problem to solve the radiative transfer equation and produce a profile that contains both the chromospheric non-LTE transition plus any set of LTE lines that you define. Okay, so then let's start with the program that I create. So we are going to be, let me show you. So as always, we are inside RH distribution, RHF1D, and then this folder is called Kurucz config1. And here we have a set of files that we will cover in today's class. And I will run ideal script as always, and we will call RH from that script. Okay. The idea is that I always run this at the beginning. I think it's maybe not necessary, but as there are some instructions in the keyboard.input that can read files from previous computations, I prefer to remove everything that was created by RH in a previous run to just start from zero and to be sure that what I'm telling the code to use is what I really want to use. Okay. So today's example, so to show you how to compute lines in LTE, what we are going to do is to run RH in non-LTE for the calcium 2 8542 transition, as we did in previous classes. And we will add LTE lines that fall in the wings of the line. So in order to make a more accurate computation of that spectral region. Okay. And we will mainly focus on understanding the information contained in the Qrx file. Okay, and as I said, it's used for providing the atomic information of the spectral lines that are going to be treated in LTE. And as we will see later, this is essentially similar as what we did for SER when we used the lines file where some atomic information was contained there. And also we had the grid file for explaining the code, what was the spectral range that we wanted to use and the sampling. Okay, so then let's start with the input files. First, we will have what I would say that is a master input file that is called Kurucz.input. Here is the example. So it will look like this. It's a blank file where you put some names. And here, as I said, you can have any set of multiple names that start with any name you want to have and finish in .kur. and you can choose it to do it in a different way. So you can have all the transitions you're interested in one file, or you can combine different files if you want to have separate, so more organized things. So imagine that you are going to treat the iron pair at 630, the calcium line, and maybe you also want to have the 1.5 micron. So if you want to have these in separate files, you only need to have here different entrances, and then the code will read it. Okay. So in our case, as I wrote here, we will use 3 files in this tutorial, although today we are going to use only 2. And this one, this is a Kurucz 8542 because we focus on this region, and then short that I will explain what is later. And next week we will use this one that is not included in the folder of today's class yet. Okay, so then let's start with the basics. So why it's called Kurucz? So the idea is that there's very, very nice database that was created by this author. So then we are using it, and then Han just call it Kurucz, so in order to refer to this database. And the idea is that you can go to the database. I put here the link. So if we go, you will see something like this. So there's a lot of information, and I recommend you to read it. But you can start, for example, with this GF100 that you can see here, the description, that is packages with the atomic information of different transitions, and they are separated in 100 nanometer packages. So we go there, and not now, sorry. And then you will see that there are several packages, and the idea is that this index, it refers to the longest wavelength that is included in the file. So as we are interested in 150 nanometers, we need to open this one that reaches until 1200 nanometers. And if you open it, you will see a lot of things. Okay, so then let's go back 1 second. This is what I was saying. And the idea is that we can scroll down until we reach the calcium transition. But before doing that, just let me bring what is included in the README file of the Kurucz database. It's in the web page in the same link. I put it here. There's a README in the lower part, but I copied here. So you can understand what is included in each column for each line. And here there's more information. So then the first value, that is the one we are going to use as a reference, is the wavelength, and it's in nanometers. So then if you want to go close to the, yes, 1 second. If you want to go close to 850, sorry, you have to go like this, and then there's a lot of line. So then you can see that 854 2. Okay, so you go more or less to this line, and then you can check lines before and after that. Okay, I will do it carefully, but just let's continue trying to understand how you can determine if the line you're seeing is, for example, the calcium 2 line. So then we found, we found a wavelength that is close to the one that we are looking for, and then there's different values. So in order to understand what is, if this is the element that we are looking for, we need to look at the third column, and then you can see that it's 20 and then 2001. So in the case of calcium, it's 20, but they added 2 values that are for the ionization stage. So then 2000 is calcium 1 and 2001 is calcium 2. Okay, so then in this case, if you want to look at the transition of interest of our example, is this one, where you can see that it's 2001. And then you have additional things like energy, the information of the level. So you can check the README and also the notes that I copied here to understand what is the meaning of each thing. Okay, it's important because this is, I think, is not stated specifically in the README file, maybe somewhere else. But the idea is that when you are looking at these transitions, these are energies from some level, and then the energy of the other level. So then in general, you would say that the first entrance will be the lower level of the transition, and the second entrance will be the upper level of the transition. But this is mainly in the NIST database. But here, sometimes you have cases like this one that is close to where we are, where the first entrance has a level with higher energy than the other. And this is because the database organized the appearance of the levels, or which one enters first or appears first, based on the parity of the level. So just to be sure, for RH, you will not change almost anything. But if you are going to use this for publication, or if you're going to use it for zero design, just be sure that you understand which is the lower level and the upper level of the transition. And also, if you plan to compute the enhancement factors due to collision with hydrogen, you have to be sure that you understand which is the lower and the higher level. And the rest is relatively easy to understand. Okay, so then for simplicity, because it's really easy to add lines to RH computation, we are just going to pick all the lines that appear in the database from a given wavelength region. So for example, from these 853.5 nanometers to 855.1 nanometers, okay? And I put this on this file, okay? So if we go here, we will see that it starts where I said that we could start, and then we have a lot of lines, and then it finishes here. And what I did was just go to the web page and then copy this and just paste in a blank file. Okay, so then it's really easy to do it. So just for simplicity, we are going to start this way. But the idea is that there are 199 transitions in this wavelength range, that if you look at the atlas, in principle, it looks like a lot of transitions. So I make a plot. I downloaded the atlas. Remember that I usually use the BAS 2000 database. So you can just put a given wavelength range and then download the data. So this one is the one I'm going to plot today, and the one we are going to refer to for comparison. The idea is that here, you have two strong transitions and maybe additional 3 here, and then some things, but 199 seems like a lot. So let's see how it looks. Okay, so the first plot of the atlas is here. Also in the folder of day 5 will be there. So this is the region we are going to use for comparison. Okay, and as I said, we have mainly 2 strong lines here and then 3 here. Okay, so then let's go ahead and then but yeah, this is what I was trying to say. So my advice is, even if it's so easy to copy lines and just run the code, you don't need most of the transitions. So this will make the computation much slower. And also, it's good to really know if you need that transition or not. And later we will see why. But my advice is to be careful, and instead of copying everything, try to go small and try to pick just a few transitions. Important thing, as in the README file, you will see here that it says it has a 160 column file. So then the .Qrx file, we are here. It's also coded to accept 160 columns. So be careful, because sometimes the editors add or remove spaces, and then you have less columns or more columns than that value, and then it will make the code crash. And in fact, I will show you today how to make RH crash, just changing some things. I see Hannes is smiling.
That's really the only way to crash it.
Yes, yes. So yes. So then the first run is just to run the previous, so last class computation. It was a file model, if you remember. It was very simple, and we spent some time preparing the non-LTE atom, a calcium atom, for making the computation. And we are just adding this file. So we go to the Kurucz database, we copy that, as we said, we copied in this file. And then you go to the Qrx.input file, that is this one, and then you tell the code that you want to use it. And also you go to the keyword.input, and there's an entrance related to Qrx files that you can find here. Yes. And there's here there's an entrance that says Kurucz data. So then you tell the code where is that file. So we are running locally. So I'm telling the RH that it's in the same folder, but just be sure that you are pointing to the right Qrx.input file. Okay. So then let's run the code. In this case, I'm just running RH. I'm not reading the file. I'm not reading the output or anything, just to check that the code runs. Sorry, just let me remove this stop. Okay. So then we will run RH, calling this extra file. Okay. So then you see that this is similar as before. So it had some non-LTE iterations. It was for calcium, and the convergence was good. Okay. If we go back a bit, there's here. There's a sentence that says that is reading the file that we are providing, and it's considering 199 Kurucz lines. Okay, so then if you see this, then the code is working and it's reading what you have in the Kurucz file. Okay, so now what I said, let's do something very simple, like, yes, let me remove this 1 second. So if we are here, you see that columns is 160 here. If we add one line and just save, then RH crashes, and it says that in the Kurucz lines, it had a problem. And the message is that, but we know what we did, so just don't do that. And the same here. So we have 160 points. So if we add like spaces until 164, if we run again, then there's a crash. So then just go back and then be careful. For example, if you want to add an extra line for any reason, you can have it like this. And I think this will work. Sorry, without a space. Okay. And yes, you can add extra lines or doing other things, and the code will not complain. Okay. So then the message here is just be careful with what your editor does. So if your editor adds or removes things, just be careful, because the code will crash, and sometimes it's not so easy to understand why it crashed. My advice here was an example of what I did. My recommendation is the first time, just add any Kurucz file that is included in the RH database, run it, check that it works, and then modify that one. And if the modification doesn't work, then you have some hint to check where the problem comes from. Okay. So then now let's go ahead. So I remove the stop here, and we run RH, and I will run it several times today. So I made like a space for how I run the code, and it's the same. So we run RH, we solve ray for computing a given heliocentric angle, in this case, this center. We read everything, and then we read also the intensity computed with solve ray. And this is the one we are going to use for comparing with the atlas. I'm also adding below each RH call the configuration we are using. So far we are using some Kurucz file, that is this one. And inside the keyword.input, we will go back to this, but just let me show you. So in this case, it says additional wavelengths, and I have nothing here. So everything is commented. So we are not using anything in wavetable. Okay. So If we run the code, then I read the wavelength, I read the intensity, and then I'm going to pick a wavelength where I'm going to normalize to the same wavelength as the atlas. Let me go back 1 second. Sorry for going back and forward. So I decided to normalize the atlas to more or less the beginning of the spectral window that I'm plotting. And this is 853.52 nanometers. So I'm going to look for that position in the RH profile to just normalize in a position that is as close as possible to that. So if you remember, I think 2 classes, or the last class, I said that you need to do that by hand. And I think Ryan and Alberto, they said, well, you can use where instruction, and it's true, and I'm including here. But what I wanted to say is that, as you will see today, if you add a wavelength vector, if you change a non-LTE atom, the wavelength file, the index and the relation between this index and the wavelength is changing. So you have to always double check that you are really picking the spectral range that you want to use, or if you are normalizing like we are going to do today, that you're normalizing in the exact position. So let's go step by step and you will see what I mean. So in this case, I'm just telling, please tell me where the wavelength vector it's smaller than 853.6 and larger than 853.4, because I don't know exactly how is the sampling, because remember that we had a coarse grid in the wings. So I just want to know if there's some value around here that I can use to do the normalization in a similar way as we did with the atlas. And then you can see if you print, there's a print here, and it says that there are 3 points in this wavelength range, and there's one that falls very close to the one I used for normalizing the atlas. So this is the one I'm going to use. So I'm not normalizing the synthetic RH profile in a wavelength region that is the same, almost the same, that I'm normalizing the atlas. So then the comparison will be as the best possible we can do. And this is basically what I'm doing here. And then I'm normalizing the intensity profile by the intensity at that position. Okay. And now we are going to make the plot. Okay, so there's a stop here. Let's go. And it goes ahead and it finishes in 293. Yeah, here. Just before seeing the plot, there's a commented line here. So I did this and then I saved the file. So this is the one you have locally. In order to avoid confusion during the class, I'm not saving it now, but the idea is that when you run the program, this result is the one you should save here as a case 1. And then I'm just restoring it, and then I'm making a plot of the atlas compared with the with the RH profile. In this case, the non-LTE computation from calcium plus all the spectral lines included in the spectral window that we are plotting. So let's go to the folder and let's plot it. Okay, so then black is the atlas and orange is the computation. Okay, so then the first thing that you see is that it's very close in the case of the calcium line. So you see the wings are very good, and this normalization, it seems that is very, very good. But we are missing most of the spectral lines, and there are also some things here and here and here. Okay, so then just let me make some zoom. Okay, you see this and this. Okay, so then let's go step by step checking what is happening. I remove the stop here, and then I said here some issues are taking place. So then the first one is that we don't have enough spectral points. Let me go back in the wings. So if you see the orange dots, they go like this, and then you have only 1 point here, and then here in fact you don't have points. And this is because we worked on creating the grid for the non-LTE transition, and we spent a lot of points here, and then here we had a coarse grid because we were not interested on any non-LTE transition here. So then in order to solve that, we are going to provide an additional wavelength vector. And this is what we saw in the keyword.file, keyword.input file. And the reason is that, so this makes sense because you don't need to solve the non-LTE problem there, but you need to have wavelengths. So then it's easier to provide it in a separate file. So then let's learn how we can do that. So let me see. Yes, this is what I said. Okay, and then this is done in the keyword.input file through a wavetable. Okay, so we go to the keyword.input, and as I said, it was commented. Okay, I will uncomment it now, and let's see how we create this test1.wave. So I copied the example from the manual, but let's cover it here. And the idea is that it's relatively simple. So you just think on a wavelength range that you want to cover. As a starting, let's cover the full wavelength range for the same plot that we are doing. And so you can define an initial wavelength, a final wavelength, and then the spectral sampling that you want to use. I'm using Armstrongs because I'm used to that unit, but remember that later on you need to transform it back to nanometers because it's the unit that you use with the Kurucz database and also with the RH. So then you can just compute how many points you need for covering this wavelength range with this spectral sampling, and you just define final wavelength minus the initial wavelength divided by step. And then I use this long instruction from IDL because it's needed if I'm correct. So just be careful if you are using Python. Maybe there's a way of reproducing this this instruction. Okay, and then the wavelength vector is simply the number of points that you need for covering it times the step that you are going to use plus the initial wave. Okay, and then we put this wavelength vector back to nanometers, and this is the instruction that is included in the manual for writing the file in the proper format for RH. Okay, so we just copied it and work with it. Okay, so then we have this. Now let's run again RH. This is exactly the same as before, and I added again at the end what I use as a configuration. And you can see that now wavetable is different. Now we are providing one, and we're using the same Qrx file. Okay, these will be the same. So you will have that I define the wavelength as the spectrum.lambda structure, and then the intensity. I'm looking for positions in the same wavelength range, and then just let me put a stop here. We can run this. Let me see if it stops. Okay, so you see that is much slower. Oh, sorry, as we are going to run it several times. Let me go back, and I will comment this. This is for today's class, but then I will uncomment it later. So just comment this, 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 and this, and this. Okay, so now the run, you will see that it takes much more time because we have much more wavelength points, but it works. And the idea is that we were here. So now the number of positions between this wavelength range, it's much larger. It's 100 points because we have created an additional wavelength file. So this is what I really meant before, that every time you add new things in terms of wavetable, in terms of changing the non-LTE atom, your wavelength vector is changing. So just always be aware of that. Otherwise, you will be mixing things when you are doing multiple runs. So then in this case, I look it by hand, and then I found that the index 63, it's also reaching the same wavelength that we had for position 1 in this case. So we are using the same value for normalizing as well. Okay, again, I don't save it here. I just go through it, and then I'm restoring here. But in your case, when you run it, please save it or just use the one I have. And then let's put a stop there. So we go ahead Yeah, it finished and now it's 490. Okay, so then now we go one step ahead. So we have, now that things look much better. So let me make this a bit bigger. So black is the atlas, orange is the initial computation without wavelength grid, and blue is the computation with the Kurucz file, with the lines information, plus the wavelength grid. So then you can see that now the lines like this one are very well reproduced, while before orange was not doing anything. Here is not working so well, so we will cover this later. Here is essentially the same, and again here is much better. So then, in fact, you really need to have spectral points in order to reproduce the spectral lines. Okay, so then let's go one step more. So the idea is that, let me see if I say it here. Yes, so the main problem is that we have improved a lot, sorry, this transition, for example, and these ones, but you see this bump here that it's not so clear what is that, and then there's also transition here that in the atlas is not present. So my advice is, as I said before, to keep it as simple as possible, and then this means that instead of adding all the lines that are present in the database, to do it in the opposite way. So just find the lines that you think are strong and just pick those lines. It means doing it by hand, but as you can see here, there are basically 4 or 5 transitions that you may be interested on. And then those transitions only are the ones that you should put in your Qrx file. So then let's do that, and let's see if this improves the results. So in this case, I'm doing it here. Yes. So we change. So we remove most of the lines from the Kurucz file. Remember that this one has 199 transitions, and this one we have only 1, 2, 3, 4, and 5 transitions. Okay. And we picked this almost by eye. We checked the one that were strongest and we picked them. There's always room for improvement, or if you want to add additional ones. But let's see what happens now that we reduce the number of wavelength points. Just let me go back, because this may crash if I run it again. So just let me comment everything. And then this one, this one, this one, this one. Yes, and we move now to the third computation. So we are running at H again. And now what we are changing is that in the Qrx.input file, we are changing the file we are using. So let's go to Qrx.input. Let's uncomment this one and comment the other. And now we run again. It's the same procedure. So we read the wavelength intensity. We look for the positions in the wavelength region to have a precise normalization. And in this case, it's the same wavelength vector, so we don't need to change anything. And we just run until stop here. Okay. You will see that, yeah, it goes, yes. And this is line 505, that is here. Okay. So let's go to the figure 3. Okay, so now let's check the colors. Atlas is black. Case 1 is 1 without wavelength grid. Case 2 is case 1 plus wavelength grid. So we're adding all the lines in the Kurucz database plus wavelength grid. And case 3 is the same wavelength grid, but adding just a few hand-picked spectral lines. So then you can see that we have good accuracy for this line. This line seems to be on the same essentially as before. These lines are good, are basically the same as before. So this is a good solution. But interestingly, we don't have this bump here that we had before, that it seems that it's not realistic, although this one is not here and this one is not here. So we are matching closely the atlas, at least in these regions. Although, for example, this one, well, it was never there. But for example, this one was in the previous one, and now we are just only matching this one. And in this case, we are basically doing the same. So then my advice in this part is, although it's very easy to just pick lines from the database, don't do it. So I mean, just try to, unless you are going to cover a very, very, very long wavelength range, just try to focus on the spectral regions that you are interested in, on the spectral lines that you think that they can help complementing the calcium line, and then just pick those ones. Because if you picked everything, you can have artifacts like this one, that it may be some log GF value that is not correct for a transition, and is making this complicated thing. Okay, so then so far so good. So then there's one last thing that I want to do today. Again, let me comment these things here to just avoid making some mistake, and then I will put it back for the file that I will share with you. The idea is, it is true. Let me go back, yes, to the file here. So it is true that now we are improving what we had before, but at the same time, if you remember, we spent one class checking how to define the non-LTE atom. We said we had Q core, Q win. That is how we distribute the wavelength points in the non-LTE dominated region of the spectral line, and we could define a coarse grid in the wings. But now what we are doing is giving a uniform spectral sampling of 20 milliangstrom, that is a lot, from here to here. And essentially we are computing 1, 2, and 3, 4, 5 lines. So we are basically doing the opposite that we did for the calcium, for the atom, for the non-LTE atom. So then let's improve what we have now, just focusing on having spectral points on the regions where we have photospheric lines that we want to solve in LTE. Okay, so then how we do that? So this is what I call a tailored wave file. So we can add packages of wavelengths as we did before, just centered on the transition. So we have here in the Qrx file, just 1 second, because Zoom is in the middle. 1 second. So yeah, so we have 5 lines, and these are the central wavelength of each line. Okay, so then if we go here, we can say, okay, for the first line, we define the center wavelength as we did before, but the initial and the final wavelength is, for example, a region that is plus minus 3 angstrom. Sorry, yes, nanometers. Sorry, nanometers. Is it nanometers? Yes. No. Yeah, it's nanometers. I will change this. And then no, it's angstrom. Yes, sorry, it's angstrom. this is from here. So in general, photospheric line in the visible or in the red part where we are now at 150, in general is not wider than this range. So just you can define this value, although you can change it. But the idea is that you will have now a wavelength vector that goes from the final wavelength, that is your central wavelength transition, plus 0.3 angstrom minus 0.3 angstrom, and divided by the same sampling as before. And then you will have a number of points. In this case, I'm putting an index 1, and then you will have a wavelength vector that covers this region with that spectral sampling and started in this wavelength. And then it's also with an index 1. So then we just repeat that for all the lines, and then we'll have points 2, wave 2, points 3, wave 3, points 4, wave 4, and then the final one, points 5, wave 5. So now we have 5 wavelength range vectors and 5 points vectors. So then we just add them into a single wave file. Okay, so it's this one and this one. Okay, and then we just repeat what we did before. We put it in nanometers and then we save it. Now in this case we call it test2. Okay, so then before running the example, I think this may seem frightening. I don't know if this is the word, but if you remember from SER, we had to do always the same. So you remember that in our case, in one of the examples, we had a 1.5 micron line. So we had to provide an index. And then we have always to define the initial wavelength, the sampling, and then the final wavelength. And we have to do all this for all the lines. So here is basically the same. So if you have lines that are far apart, like more than 1 angstrom, then it doesn't make sense to cover all of the lines with a uniform spectral sampling, because you are spending computational time on regions where there's no need to solve the radiative transfer equation with a high spectral sampling. So then it's very similar to SER. Just give it a thought. And if you don't understand something, just let me know. Okay, so then let's run the code. Again, this same call to RH. Here we have the information. So then let's see. So it should be short in the Kurucz.input file. So like this. And then in the input file, sorry, in the keyword.input file, it should be the wavetable test2. Okay, so like this and like this. Okay, so we run it. Again, we have a spectral, sorry, a wavelength vector, the intensity. We look for positions, and then the value could be a given one. And we check that is where we want to have it. You can see that now it's much faster. So we are having LTE lines, but it's much faster than before. And you can see that it says that index 1 now in this region, it's providing the same wavelength value as before, so we can use it for normalizing. And then again, I don't save it, but you should save it when you're running it. And then I will make the plot of that, and I will do a double check where I print all the wavelengths that I'm using for normalizing. So we will see it now, just to be sure that for any case study that I did, where I changed the wavelength vector or the number of points, something like that, I'm using the same value for normalizing. So in order to avoid discrepancies between the results. So then we go here, and you see that all of them have the same value, I hope. Yes, although the points are different. And now let's see what we have. So let's go again to, let's make a zoom, to colors. So black is Atlas, orange is the first case without wavetable, blue is the case with Kurucz, all the Kurucz line and wavetable, 3 is the case with only a few lines and the same wavetable, and 4 is in principle the best case with only a few spectral lines and a selected wavetable optimized for the transitions of interest. So then the best line that we can use as a comparison is this one. So you can see that between blue, red, and red, and yes, red, blue, and yellow. So they are the same. And this is good because it means that we are not missing anything in the last step. We have less yellow points here, but this is good because we don't have them there. Here is the same. And then here we have only a few yellow points, but are matching the red one that we thought that is the best solution. And they are far from orange and blue that are when we use all the lines. And then in this part, we are also matching the previous solutions with good accuracy. So then we have only a dense grid for the LTE lines that we really want to solve. This one, and then these two. Okay. So just let me, in order to clean this a bit, let me see. Yes, so let me show you. So I did a last plot that is just the final configuration, so the yellow one and the black one. So here you can see that this is probably what I would say that you should use for the computation. In this case, you may add more points if you want to have a bit larger wavelength region. Maybe I will do it for next class. So the idea is that it looks really good. So these two and these two and this one. So until this point, I think this is the best we can do in terms of RH configuration. So for next class, what we are trying to improve is, for example, this case. So we have a transition that it seems that is the one that is there. And we are using the value from Kurucz, but as you can see, it doesn't look like the atlas at all. So then we will try to experiment or to check if there are some publication that has an updated information regarding this atomic information of the spectral line, and if this may improve the computation results. Okay, so I think this is basically everything before summary. Yes, this is what I was saying, that this line does not look okay. So then we will check next week, and then we jump into summary. Okay, so let me do the summary, and we can have questions if you have any, and if not, I will go to the presentation. But the idea is that we have done several steps because I wanted to show you exactly what is happening, and I hope it's useful. So the idea is you can add multiple Qrx files with line list inside in RH. You can have only one Qrx.input, but then inside you can have several. And the idea is that you can put lines there. But although RH was designed to just have everything from the database and put it there, I think it's not the best option because as you saw, there are some cases where it seems that it's not reproducing the atlas and it's doing something wrong. So I recommend you at least at the beginning to just pick a few strong lines that are the ones that are going to really help you determine like the magnetic field in the photosphere or constraining velocities in the photosphere. Weak lines, they are probably not going to do anything, for example, in the inversion. So just focus on the strong ones that they may be helpful, and also that usually are better defined than the weak lines. Okay, and I think there's a question. Yeah, that do you want that I finish the summary or you prefer to ask now?
Yeah, I'll wait.
So then I will finish and then we can go to the question. So then and then when we had the final handpicked lines, we can also make a tailor-made wavelength vector, just putting spectral points on that line. And later on, if you add a new line, you just add a new sentence in this case, for example, here. Imagine that you add a new line, so you just copy this, a new entrance, and then you create a new file, and then you run the code again. So it's really relatively easy to build things, and it's much easier than trying to look which of the 199 transition is making a problem. So I will do it in a different way, and then optimize your computation with a tailored wavelength tables for the lines of interest. And then this is for just for next week class, and this is what I said. Basically, we cannot do, I think, anything more for improving the computation of those lines in terms of RH. So if they are far from what we have from the atlas, it means that something is not very accurate in the atomic information. And then this will depend on what other people have done or what we can do for that. And there are several things that we will study next week. Some of them are the easiest ones that are just changing the log-GF value, but others are improving how we solve the transition, because usually we are assuming LS coupling or Russell-Sanders approximation, but now they are RH and also design, they accept more complex mechanisms that are very important when we add also the magnetic field and we have the sigma splitting. So then we will continue adding things that will improve, definitely, but still having very good results sometimes will not depend on us, will depend on how accurate some atomic information, atomic values are defined. And sometimes this is evolved and sometimes it's not very evolved. But still, I think we are in the right direction, and next week we will improve. But of course, there's always room for improvement. Okay, so yeah, so that you can ask the question.
Yes.
Yeah.
So if we identify the wave grid, not wave grid, the wave table.
Yes.
If we specify the wave table in the keyword input,
yes,
and does the code completely ignores the Q core and the Q wing in the atom file?
No. If I think it's priority. So I think the code starts with the atom and in the information you provided in the atom, Q core, Q win, and then it adds the spectral information that you are providing, and it checks, in fact, if some of them are in the same position, and then remove it. But the idea is that they are just combined. So if you have, like, imagine that these are spectral positions, and this is from the atom file, and you have a new vector that it has one position that falls in the middle, then RH will use the 3 points. But if you have like two, one is falling on top of the other, so then I think this is what the code is saying here, that is just taking the ones that are not duplicated. Is this correct, Han?
Yes.
Yes.
Yes. It just adds the wavetable wavelengths just get added to the ones that are derived from the atom files.
Yes. So you basically can see it here. So this is coarse, dense, because we defined it in the atom, and here it was a coarse grid. So you have these points, but then here is where the wavelength grid starts, and then you can see that there's very dense here, and then it stops where we said that we don't need to have more points, and then it's a coarse grid again defined by the atom, and then again the new one defined by the wavetable. So it's essentially combine them. But for example, I'm almost convinced that 1 or 2 points of the atom grid, it's falling, and they are falling here. So then this is why RH is saying there are few wavelengths that are duplicated. So then those wavelengths are removed. But in fact, so in general, it will combine both to have the best configuration.
So in this case, we no need to define this wave position while defining this wave table at this NLTE, non-LTE line, right? Because it will automatically take this denser points, let's say around 8542 from our Q core and Q wing values.
Yes. So can you repeat again, Nancy?
Okay, so now as you have showed, you define the tailor-made wavelength grid for these 5 lines.
Yes.
Like centered around 5 wavelength positions.
Yes.
So if RH is just combining the previously given Q core and Q wing,
yes,
and this wavetable information, so in this case, we no need to define this wave information at 8542, because it will automatically take this denser grid around 8542 from that previous information.
Yes, yeah, I think I understand. So the idea is that when you have the non-LTE atom solving the transition, in fact, you don't have that information in the Kurucz file. So I'm sorry, yes, 1 second. So here we have the information of the LTE lines, but I don't include here the calcium line. So the calcium line is defined in the non-LTE atom, so you don't need to have any LTE related information there.
Okay, fine, yes.
If you would add the non-LTE line there, it would actually be ignored, because the code checks for lines that are the same.
Yes.
It will only use them once. So if you have them in both places accidentally, then So if you would add that, it would not change anything. Hopefully, hopefully the
Yes.
code. It's not easy to do, but the code tries to check
Yes.
whether the lines there are lines close enough from the same ionization stage.
Yes. 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 In principle, this is the calcium 2 line. So if you add it here, I didn't check it, but maybe this can be a good exercise as a homework.
Yeah,
but if you add it here,
yeah,
in principle, it should not do anything. So because it's already solving it in the non-LTE part. So I think the step is first the non-LTE atom that will, for example, in this case, let me go. In this case, you have the calcium line, and then you focus only on the regions where you have photospheric lines that are of interest. If the photospheric lines falls here, then you may play a bit, because, for example, here we are outside the dense grid, so maybe you can add an extra wavelength table for this region. But for this part, it's essentially non-LTE and is defined by the atom, so you don't need to add extra points for the non-LTE solution, just for the LTE lines that are defined in the Qrx file.
Yeah, okay.
Okay.
And sorry that was jumping into your question.
No, it's fine. It's fine. It's fine. It's good to have questions. Thank you. Okay. Is there any? Yeah.
Yeah. One further thing to point out and maybe make people aware of that the wavelengths in the Kurucz file are air wavelengths.
Yes.
So if you would try to compare that with the difference in the energy level converted to an energy to a wavelength, they wouldn't match. So you have to be aware of that. And the RH has a flag that is usually set to true, that you convert the output wavelengths also to air wavelengths. Then you can easily compare with Atlas. But you have to be aware that wavelengths are sometimes in air and sometimes in vacuum.
Yes. This is from the README file of the Kurucz database. Then what Han is saying is somewhere here. So let me see where I have it. Vacuum to air. So then this is a very good point. Thanks, Han. So the idea is that these are in air. So I'm comparing the Kurucz files with one that I'm using. So when I define the wavelength vector, so let's go to the case where we really had specific. So in this case, I'm defining a wavelength that is referred to the Kurucz file, and then I'm defining a wave vector. But if you go down, you will see that I'm using air to vacuum in the sentence. So I'm giving this to RH as a vacuum wavelength, and then I'm telling in the keyword.input to use vacuum to air true. Okay, so it's just to this means that we know what we are doing, although we may be changing one and the other.
Well, so internally the code has to work with the vacuum wavelengths, of course, because you depend on energy differences converted to wavelengths, etc.
Yes.
So internally, all the calculations are done at vacuum wavelengths.
Yes.
And then on output, they're converted to as they should.
Yes. So essentially, is that so we work on air, we transform to vacuum, and then we ask RH to give us back air with this sentence. Okay.
I guess in principle, RH could have done the conversion reading the wavetable in air and then
but I think it's fine. I just be aware of that, but in principle, just at least with one example, just check that the numbers make sense, and then you can be safe. And yes, okay, so then there was a final note. Yes, so just that when I was doing the class, I was not sure if I should have everything in one file, one after the other, or just have multiple folders. I decided one folder, but if you realized I'm calling RH several times, but in each time I'm changing the configuration of RH. So I put it after each call, the configuration that I changed, so you can easily check it, but please double check it, because if you mix one Qrx file with a wavetable, then the results will be different. So just be sure that in each case, in case 1, 2, 3, and 4, you really are changing the Kurucz.input and the keyword.input file, and then don't overwrite some previous runs with this new configuration. Okay, and I think that's all. Okay, so then there's any additional question before going to homework? No. Okay, check. NLTE line. Okay, so then try to run the test. As I said, I think it's a bit long, but I wanted to have it very so with increasing steps, but very slow increasing steps, so you can really know what is happening. So you just change one thing in each time. Maybe you would like to create a new Qrx file. As I said, the editor can change the format, so play a bit, just change something and then try to run it, and if it crashes, then maybe something is happening. And also, please take a look at the README file of the Kurucz database. We will not use it in the case of this site, because the information will be provided through the site to RH, but some of the things we need to extract it from NIST or from the Kurucz database. So it's always good to have some options to know where you can look at the information of a spectral line. So because sometimes the NIST is not complete, so the Kurucz is always a place to at least double check if there's some transition that falls close to what you see in the atlas. So try to get familiar with it because it's very complete. We saw that in some cases, some parameters doesn't work very well, but in others, they work great. So try to get familiar with it, because it's a very valuable resource. Okay, so then next class, we will continue. As I said, now what is remaining is to play a bit with atomic information. It could be either the log-GF, it could be how we treat the transition, and sometimes it will improve, sometimes we will have to live with what we have. But now it's something that is not strictly dependent on us, but at least we will check what we can do, and hopefully in the future we will have always option to improve. Yeah, it's basically what I said. And yes, every time that you improve the transition, that is very important, because it's not only for RH and for your topic, it will be for everyone in any field that is using those transitions, in solar or even in other areas. But at least every time that you find a better log-GF value, at least people using SER, RH, Desire, Stick, or Nicole, I forgot to put it, or Nicole, or the code, Snappy, they will be able to have a better atomic information that definitely will help the inversion results. So everything we do here, if we do it together, it's always good, because it will have an impact, a positive impact on everyone. Okay, so then next class on next week on September 3rd, Friday. And if there are no more questions, so please enjoy the weekend. Okay.
Thank you very much. That was great.
Okay. Okay. So thanks a lot, and see you next week.
Bye.
Bye.
Bye.